Now, the lanthanoid doesn't shows variable oxidation state. The reason being the energy difference between 4F and 5D6S subshells is very large. Energy difference between this 4F and the 5D6S is very large. As a result, we can't get 4F electrons involved along with the 5D6S electrons. So what we are left? We are left with only 1 and 2 electrons in the 5D and 6S. So all lanthanoids are having plus 3 as their most common oxidation state. That's their most common oxidation state and most stable oxidation state. Most stable oxidation state. We have elements of lanthanoids which are existing in the different oxidation states, but yes, again, their plus 3 is their most stable oxidation state. Let's talk about cerium, which is having a configuration of 4F1, 5D1, 6S2. It shows plus 4 configuration where it requires 4F0, 5D0, 6S0 configuration, where it is having a pseudo noble gas configuration and is very stable. But remember, it will be acting as a good oxidizing agent because it gets changed to cerium plus 3, which is its most common oxidation state, and that is why it is used as an oxidizing agent also. Cerium as such, as a whole also, is a very good analytical agent also because its redox reactions are kinetically slow, so we can do a lot of manipulations with that. That is why the cerium plus 4 is a very good, we can say that plus 4 in plus 4 oxidation state, it is acting as an analytical agent also. In oxidation states, let us take some other examples, like we have europium, which is having a configuration of 4F7, 5D0 and 6S2. Therefore, very easily it shows europium, it shows plus 2 oxidation state where it acquires half-filled stable 4F7 configuration and 5D0 and 6S0. Similarly, we have ytterbium, which is having a configuration of 4F14, 5D0 and 6S2. Atomic number is 70 in this case, in this europium. Now this europium, therefore it shows plus 2 oxidation state very easily where it acquires a pseudo noble gas configuration of 4F14, 5D0 and 6S0. So these europium and ytterbium, which are existing in plus 2 oxidation state, they will be good reducing agents because ultimately they will be getting oxidized to their plus 3 oxidation states. So this is what we have, the details about the oxidation states of the lanthanoids. Now let us talk about their general characteristics, general properties. General characteristics. See, lanthanoids are silvery white metals where they easily get tarnished in the air because of their oxidation. They are very reactive metals with their E0 reduction values ranging from minus 2.2 to minus 2.4, except one exception of europium. Otherwise, they are having usually between this much is the range, which makes them quite strong electropositive in nature. They have high ionization enthalpies because of their poor screening of the 4F electrons. And that is why what we find is that the first ionization energy is usually of a range of 600 kilojoules. The second energy is of the range of 1200 kilojoules, and third one shows a lot of variation. The reason being then the electrons then rearranges themselves. But yes, they have high ionization enthalpies. They form light colored compounds. Whenever they have unpaired electrons, those electrons shows FF transitions. But the range is very narrow. The reason being because the transitions are within the F orbitals or F subshell. That is why the range of the color is very narrow. Then let us talk about something about their chemical properties. They all react with the non-metals at fairly high temperature, but they react and they form number of compounds. Like this lanthanoid, when reacted with carbon at around 2500 degrees Celsius, it forms carbide with the formula LnC2. With acids like HCl, others, it forms LnCl3 plus and releases hydrogen gas. I'm taking Ln as a common symbol of lanthanoids. It can be any one of those 14 lanthanoids. It combines with halogens to form LnX3, where X can be a fluorine, chlorine, bromine, iodine, any one of these. It combines with water and forms the corresponding hydroxide OH3 and releases hydrogen gas. It combines with oxygen and forms lanthanium oxide Ln2O3, and it can combine with sulfur to form Ln2S3 lanthanium sulfide. So these are its common reactions with the non-metals, which takes place at a fairly high temperature of around 300 to 400 Kelvin. Now, after studying the general characteristics, we must know one very important use of these lanthanoids. They are used to prepare an alloy called mish metal, which contains nearly 95% any of the lanthanoids, mainly cerium, approximately 5% is iron, and they have traces of sulfur, carbon, calcium and aluminium. Now this mish metal is used in making flinters of bullets, gas lighters, etc. So these are the basic, one of the major uses of the lanthanoids.